What is big data? It's a term that's used loosely, but there are some definite aspects of big data that we're going to look at. So big data is modern data, and it can be massive and messy. So what do we mean by modern, massive, messy, big? Well, we start with the three V's. So a widely accepted characterization of big data is due to Gartner that we have high volume and high velocity and high variety that requires new forms of processing to make better decisions and do better optimization. And of course, we always want to have high veracity. Veracity is how good the data is. So let's look at these in detail. The four V's of big data: volume, velocity. Data can be streaming, or just in general, the computation may need special algorithms because of the time constraints. Variety, and veracity. Now this is the four V's of big data, but we're actually only going to consider three. Why? Because veracity means how good the data is. So even big data can be bad data. And we're not going to worry about what makes data good or bad in this course. That comes from a course in what's called experimental design. So we have the three V's: high volume, high velocity, and high variety. So modern data doesn't have to be big, and we'll often use medium-sized data because our goal is really to look at high variety. We won't neglect high volume and high velocity, but high variety means that the big data we look at has a complex shape, a complicated structure. Data can be unstructured or structured and may need to be transformed before we can even begin to work with it. So what do I mean by unstructured data? This usually is considered key value pairs. Not all data is numerical. Documents can be used as data. Tweets, music, social networks, artwork, those are all data. But all data can be represented by key value pairs. Now a key is a unique identifier. You can't have duplicate keys. All the keys are unique. For example, a social security number or the timestamp of when you actually obtained a particular value. And a value is an object or a list of objects. Could even be a list of keys. So an example of unstructured data is networks. Here we have a little social network. The keys are the node identifiers, and each node has a unique identifier. And the values are just lists of the neighbors. So A has a neighbor of D, as you can see in the diagram. B has a neighbor of A. C has neighbors of F and J, and so on and so forth. And networks tend to be high volume, lots and lots of nodes. Data may not arrive as key value pairs. For example, documents are often used as data, but they're not key value structures. But you can always represent them in terms of key value structures. So a key could be a given word as it occurs in some document. The value could be the number of times the given word occurs in that document. Or the value could be a list of words that are somehow related to the given key. So automobile could be the key, and it could have values of car, truck, vehicle, SUV, so on and so forth. And usually there are a high number of key value pairs. Structured data just means rectangles, spreadsheets. We tend to call the columns features, and we tend to call the rows observations. In other words, each row is an observation of some collection of features. This is an M by N array, and the set of all m by n arrays of real numbers is denoted R superscript m by n. M is often very, very large. For example, suppose we look at word counts in the plays of Shakespeare. So the features are the plays, they're the column labels, and then you look at all the words that occur in all of the plays of Shakespeare. It's a sparse matrix. Only a small percentage of the coefficients are non-zero. Grayscale images are rectangles of pixel intensities ranging from 0 to 1. This is what's known as a dense matrix because most of the coefficients are not zero. In other words, most of the pixels are not black. Graphs or networks, these can be represented as rectangles. So our edges connect vertices, and an edge that begins at A and ends at C will have a -1 at A and a 1 at C. And we can add an edge, and this kind of an array, by the way, is called an incidence matrix. And it tends to be sparse because in general, each row is mostly zeros. In fact, every row only has 2 non-zero entries. Time series. So these are what we think of as functions of time. And of course, they're not sparse. You could have several rectangular data sets, a box of rectangles, which is sometimes called a tensor, a collection of spreadsheets. And dense, because of this, data sets tend to be large. So if you had 100 spreadsheets with 100 observations of 100 factors, that's 1,000,000 data points. For example, suppose you have movie rental data. Each day, viewers download, watch, and rate movies. And so you have a rectangle for each day. Millions of viewers with thousands of movies that they could watch over thousands of days. Now you're looking at trillions of data points. That's high volume. For example, wiki logs. A log of the number of requests per hour per page of Wikimedia, and you can find that at the wikimedia.org website. And we tend to think of it as the pages as observations and the hours as features. And we can look at the page requests or hits during that hour for those pages. That's again a rectangle, a box of rectangles. So if there are 5 million pages with 24 hours over 3,000 days, that's 360 billion hit counts. This is just the tip of the iceberg. We tend to look at high variety data, and that high variety data tends to be high volume. Large data sets, however, are not new. For example, ports have tracked the tides for centuries. We have hundreds of ports recording thousands of tides over thousands of years, but we don't call that big data. Population data, census demographics, we compute counts, averages, and proportions, but we don't tend to think of that as big data. So what do we mean by big data? Well, big data means not just large, but also complex. And complex, not as complex numbers, but complex as in sophisticated, complicated. High volume's not enough. We also have to have high variety. In fact, the high variety is what gives us the high volume. Complexity is mathematical high variety. So let's look at this data set. This is geometric features of squares whose sides range from a length of 1 to a length of 1,000,000 by 1. It's a huge data set. There's 1,000,000 rows and times however many columns there are. But this is not complex data. There's only one independent variable in the entire data set because every single column can be constructed from the first column. Area is the side squared, perimeter is 4 times the side, diagonal is the square root of 2 times the side, dimension, number of vertices, number of edges, those are all constants. We may be able to choose which independent variable that all the data is a function of, but this is not complicated. It's not complex. Modern data tends to be big data, tends to come from experiments that produce large amounts of data from a large number of highly diverse interdependent processes, where by interdependence I mean a mixture of dependent and independent variables. And this mixture of dependent and independent variables defines some kind of an underlying structure. Complex, we tend to think of as a high-dimensional interdependence. For example, let's look at microarray data. So what we have is the observations, the rows are the genes. We have 22,645 genes. And there's a certain experiment called a microarray experiment where you can measure the activity of each gene during that experiment. And so each subject, you get 22,645 activity levels. Now in the experiment, some genes are activated. In other words, some genes in your DNA are used because of something that happens in the experiment, and some genes are not activated by the experiment. So there are a lot of different reasons that genes get activated, not just your experiment, but also metabolism, respiration, DNA repair. So this is a complicated interdependence of the genes, and really the only thing the experiment is doing is introducing one additional variable of whatever the experiment is. So for example, you may have somebody who consumes a drug, and after a certain period of time, and this drug has been able to metabolize into the body, they do this microarray experiment, and then they look at what's activated and what's not. So in summary, big data is large, and most importantly, it's complex. It's high velocity. We'll see later on why we have to use certain kinds of algorithms. It's high variety, highly complicated data formats with complex underlying structures. And because of that complexity, it tends to be high volume. So often the underlying structure is multi-scale, which allows features to emerge from the system. And this is what we're going to look at next. But to conclude, for instructional purposes, I just want to point out, we're going to make our data sets as small as possible. We definitely want to study the complexity, the high variety, without necessarily looking at the largest possible data sets.